All right, guys, this is Miss Madden. This is the first time I'm trying this, so forgive me for my stumbles. But we're going to see how this goes anyway. So I just want to let you know this first slide refers to stoichiometry and says that it's chapter 9. However, in your book, it's actually chapter 11. So I know that we usually don't use our books too often in class, at least not in mine. But remember that you always have access to your textbook online. And so if you ever need extra references and you don't know how to access your online textbook, please stop by my classroom, E234, and I can show you where you need to go to get that going. So anyway, we're starting a whole brand new unit for the second semester, and it's stoichiometry. And leading up to this, it's really important that you have a good foundation in understanding the different types of chemical reactions. We've discussed 5. We talked about synthesis, decomposition, single replacement, double replacement, and combustion in some detail. And so you're going to have to be referring back to that. You also need to be able to understand balancing chemical equations. In fact, if you're struggling with that, again, please, many of your teachers, including myself, we have all of our tutoring times posted. You are more than welcome to meet us, any one teacher, during those tutoring times. So you have many resources available to you. And I'm not going to lie to you, this is a very complicated topic. And so don't be afraid to ask questions as you're going through this unit with me or your other teachers. Also, we ended our last unit over talking about converting moles. And we did converting moles to, or grams to moles, moles to particles. And so we're going to continue that, building on that, and using the law of conservation of mass. So all of these things are very much tied together, and it's really important that you understand all of these topics. And so this presentation is going to give you the first part of this. All right, so chapter 11, if you have access to your online textbook. Okay, so this slide refers to proportional relationships and bringing into mind that when we were looking at chemical equations, we're looking at the relationship between our reactants and our products, and essentially how much we need of reactants to make so many products, right? If I have 3 pieces of bread, then I can only make 1 complete sandwich based on how many slices of bread I have. And so that's kind of the idea of what we're going to be doing. Proportional is probably a word that you recognize from math. And this is where you start bringing in your other topics and your the other things that you've been learning in another class. You bring it into this class, and it's all relative. It's all related to each other. And so keep that in mind when you hear a word where you're like, hey, I've heard that word proportional in my math class. Yeah, it's the same thing. That's you applying what you're learning somewhere else. So here on this slide, we're looking at a recipe. And in this recipe, it's basically telling us that if we have 2 1/4 cups of flour and 1 teaspoon of baking soda, 1 teaspoon of salt, 1 cup of butter, 3/4 cup sugar, 3/4 cup brown sugar, and so on, that ultimately I will be able to make 5 dozen cookies. And so the question it gives us is, if I have 5 eggs, how many cookies can I make? This is kind of the same scenario I just gave you, in that if I have 3 slices of bread, how many sandwiches can I make? I can only make 1. Same idea. So when we set up our problem, we always start with the number it gives us. It gives us that we have 5 eggs, okay? But it's asking, how many cookies can I make? And so I have to go from 5 eggs to calculating how many cookies. In my first square, and remember, we're using the railroad tracks to guide us through the problem. And so in our first square, we always put the number that it gives you in the problem. And I start with 5 eggs, okay? Now, in order to solve this, I have to refer to the recipe. And when you're solving chemical equations, remember, like I said, the chemical equation is your recipe. That's going to help guide you. Now, there are steps to this, and you have to make sure your equation is balanced to make this work. We'll get to that in the next slide or two. But getting back to this problem, I have to start with the number it gives me from the problem, 5 eggs, 5 eggs. And then in order to cancel out eggs, because the question has to end with how many cookies. That's what I'm trying to get to. I know that if I have 5 eggs. And in the problem, according to my recipe, right, I need 2 eggs to make 5 dozen. Do you see that? And so I'm going to use the catty corner. You're going to go from here to here, okay? Because I want to cancel these eggs out, okay? I want my answer to be in dozens. And so I need to get to that point by making sure all my units are canceled out. And in this case, my units are eggs. So I have 5 eggs, and I know 2 eggs will make 5 dozen. So what do you do at this point? You make sure that you have all of your units lined up so you can cancel them out, just like they did with the red line there. And then the relationship, the ratio of eggs to dozen is 2 to 5. So for every 2 eggs I have, I can make 5 dozen cookies. And that's where this 5 comes from. It came from my recipe here, that if I have 2 eggs, I can make 5. And so now I have my problem completely set up. And what do you do? What did you learn from conversion? You learn that you multiply all of the top numbers, and that you divide by your bottom number. So you're going to do 5 times 5 is 25, divide by 2, and your answer is 12.5. So in the last slide, we were looking at a recipe, and we saw that if I had 2 eggs, I could make 5 dozen. And the problem stated, I have 5 eggs. How many dozens can I make? After our calculation, we were able to determine out of 5 eggs, we could make 12.5 dozen cookies. And to relate this to chemistry, we look at stoichiometry, and it's the same thing. Mass relationships between substances in a chemical reaction based on the mole ratio. This is a very large summary of what it is. So I wrote another definition, and I said, the study of the quantitative relationships between the reactants used and the products that are formed. And let's look at some of the words in this definition. I think it's easier to understand this one than the other one, quantitative. And we see another word that should be ringing bells to you at this point from science, from your math class. Quantitative is the number analysis of something, right? In math class, you're just looking at numbers, and those numbers have no meaning though. In chemistry, you are building you're bringing in your math skills, and you need to start applying what you're learning because we're giving meaning to those numbers now. We use number analysis, right, to understand the relationship of things. When a scientist is preparing to, or is going through experimental design and designing an experiment, they don't just go to the lab and start mixing this, a little bit of this, a little bit of that. What they do is, on paper, they determine, okay, if I have this many grams of reactants, how many grams of products can I produce? Or if I want to produce this much grams of a product, how many reactants do I need? And this is the math behind that, okay? So, in the lab, what we use for analysis is our observations, right? So in an actual experiment, we use our observations and data to do our analysis. On paper, though, we use quantitative analysis to understand a chemical equation on paper. All right, so understanding this relationship brings us to our next definition, that is mole ratio. Here we have that mole ratio is defined or indicated by coefficients in a balanced chemical equation or equation. Remember, these guys, the ones that come in the front of a compound, those are our coefficients, okay? These are going to tell us how many moles we have or how many moles we need to make a reaction occur. When we look at a mole ratio, we can do it in many different ways. Again, it's like reading a recipe, okay? And according to my chemical equation I have here, and I rewrote it because it doesn't have the yield sign, that should be here. Here I have that I need 2 moles of magnesium to make 2 moles of magnesium oxide. Okay, that's my recipe for this. And so my mole ratio of magnesium to magnesium oxide would be, it would be 2 to 2. Magnesium to magnesium oxide. All right. We can look at other ratios in this chemical equation. We can look at oxygen here, and the relationship to magnesium oxide. And in this situation here, we have this invisible imaginary 1, right? That is there, but it's not written, but it's there. And that's the coefficient. And then we have the 2. So the mole ratio of oxygen to magnesium oxide would be 1 to 2. What we're saying is I need 1 mole of oxygen to be able to produce 2 moles of magnesium oxide. So on this slide, we're looking at the actual steps to solve a problem, a stoichiometry problem. And as I already said, step 1 states the most obvious. You have to have a balanced equation. You can't do anything until you have a balanced equation. Remember, we use coefficients to balance our reactants with our products, and those coefficients are what we're using for our mole ratios to move from one compound to another in a Stoich problem. Number 2, you have to be able to identify the known and the unknown. Understanding what the problem is giving you and understanding what it's asking you to find is going to guide you through the problem. This is also going to help you with writing your ratio. Whoops. So when you write a ratio, you are writing the ratio of the known. Okay, sorry guys, I'm still trying to get used to this. Okay, you're writing the ratio of the known to the unknown. And it's going to go in that order. So on the last slide, when we were looking at the oxygen to the magnesium oxide, if we had a problem asking us a question, our given would have come from oxygen. So it could have said something like, you have 5 moles of oxygen. How many moles of magnesium oxide can you produce or would be produced? And so we would solve for that. And as we get into more practice, this will make more sense. All right. Number 3 is you line up the conversion factors. And in the conversion factor, there are different conversions that we're going to be making within a problem. So some of these don't quite make sense. Some of them are new. We haven't used some of the words, like, for example, we haven't talked about molarity yet, but we will. So one of the main conversions that you need for all these problems is the mole ratio. That is the coefficient of our known to the coefficient of our unknown. That's how we get our mole ratio. All right. And usually we use mole ratio when we're doing a moles to moles conversion. In a moles to grams or grams to moles conversion, we're using molar mass. Remember, we have to calculate from our compounds the atomic masses, add them all together. That's that. Another conversion that we could do is a moles to liters or a liters to moles. And we call that molarity. We'll talk more about that definition soon. And then another conversion would be moles to liters gas to moles, and we call that molar volume. The core step with this note right here, the main step that you must understand how to do is this mole ratio. Most students are able to understand it's the coefficients, but what ends up tripping you up is what order do you put them in? So remember the order I've told you. You always put the known first, and then it's to the coefficient of the unknown. Okay? And number 4, there are ways to check your answers. If the conversion that we're doing is for molar volume, the conversion factor is 1 mole of gas would equal 22.4 liters. And this is assuming STP, something we talk about standard temperature and pressure. At standard temperature and pressure, we have 1 ATM. And I know these are a lot of new vocabulary words that you probably haven't heard before. We haven't really talked about them with the on level very much. And at this point in our studies, we will only be converting. When we get to our gas unit, this will make more sense. But for now, you just need to know the conversion factor is that you have for every 1 mole at STP, this is for gas, you have 22.4 liters. This slide here basically is the grand summary of all the conversions that we do, and in this order. Notice that the arrows go back and forth because I can go from moles to grams or grams to moles. Now, in order for me to go from grams to particles would require several steps. And notice in between, one of the conversions I need to do would be converting the grams to moles first before I can then calculate how many particles that would be. So we give you basically a skeleton of which of how to format your problem. And I can show that to you on another slide, and your teachers will probably give you a little handout that shows you, okay, if you're converting mass to moles, this is how you set up your problem, or if you're doing mass to particles, this is how you set up your problem. And I'll do another one on that alone. One more thing I want to point out is that if you are doing a conversion of grams to moles, I want you to notice what number you're going to need to use. You're going to need to calculate that molar mass. That molar mass is going to help you make that conversion. Look over here where you go from moles to particles. The number here you need to use would be Avogadro's number, and this is kind of written weird, but it is Avogadro, remember, 6.02 times 10 to the 23rd. Okay, parts, particles, molecules, atoms, could be anything, right? If you're doing a conversion for liters of gas at STP to moles, then the number you need to use to make that conversion is 22.4 liters per mole. And if you're doing a conversion of molarity of liters of solution to moles, then the number you need here is your moles per liter. So those are the key numbers that you're going to need at each step to make that conversion take place. And so I hope that this helps you as we get further into it. At this point, with my students, we've only talked about converting moles to moles. We are going to start talking about mass to moles and moles to mass, and then we'll start really getting into working these problems. All right, leave your comments, guys. Leave your questions, and let's collaborate and help each other out.